In this video, we focus on one very important exception in proton NMR, alkene. At first glance, the two hydrogens on this carbon may look similar, but in an alkene, that is not always enough. A useful beginner rule is this: if two protons have the same environment, they give the same signal. Very often, protons with the same connectivity are usually equivalent. Ethene is a simple example. In an alkene, the CC double bond does not rotate freely. That means one hydrogen can stay cis to a group across the double bond while the other is a trans. Cis is not trans. Once those relationships stay fixed, the environments can become different. Let's start with the easiest alkene, ethene. How many proton environments are there here? The answer is ethene gives one signal. That's because all four hydrogen are equivalent. Because the molecule is symmetrical, every hydrogen experiences the same environment. Now, let's move to propene. This looks only slightly more complicated, but it already shows the exception. Here we should expect 4 signals. Let's understand why. In propene, these two hydrogens, hydrogen A and hydrogen B, are not equivalent. Hydrogen A is trans to CH₃. Hydrogen B is cis to CH₃. Therefore, these two hydrogens are not equivalent. One is cis to the CH₃ group across the double bond, while the other is trans. Because the double bond locks the geometry, those two hydrogens sit in different environments. Therefore, propene gives 4 proton environments in total, hence 4 signals or 4 peaks. The two hydrogens on the CH₂ carbons are different from each other. The alkene CH is another environment, and the CH₃ group is the 4th. Now, test the same idea in another alkene, 1,1-difluoroethene. Here, the carbon across the double bond has 2 identical substituents, fluorine and fluorine. So what happens to the 2 hydrogens now? Are the 2 hydrogen on CH₂ equivalent? The answer is yes, they are equivalent. That's because the other alkene carbon is symmetrical. In this case, the 2 hydrogens are equivalent. The carbon across the double bond has 2 identical groups. So the cis-trans comparison does not create 2 different environments here. Now, let's make one small change. Replace one fluorine with chlorine. The carbon across the double bond is no longer symmetrical. Does that affect the 2 hydrogens? Now, the 2 hydrogens become non-equivalent. Hydrogen A is cis to fluorine and trans to chlorine, while the other hydrogen B is cis to chlorine and trans to fluorine. Those are different environments, so they give different signals. Thus, we should expect 2 different signals. Now, let's put 2 molecules side by side. On the left side, we have CH₂ CF2. On the right side, we have CH₂ CFCl. Under the left molecule, we have 2 identical groups. Under the right molecule, we have 2 different groups on this carbon. Therefore, the hydrogen on CH₂ are equivalent, whereas the hydrogens on CH₂ are non-equivalent. This comparison is the key. If the other alkene carbon has two identical groups, the CH₂ hydrogens may be equivalent. If it has two different groups, those hydrogens may become non-equivalent. Here's the shortcut you can remember. For two hydrogens on the same alkene carbon, if the other carbon has two identical substituents, those hydrogens may be equivalent. However, if the other carbon has two different substituents, the hydrogens may become non-equivalent because cis and trans are no longer the same. In short, cis and trans do matter. Let's do a quick summary on the number of signals that is associated with each individual examples that we have gone through. For ethene, it will display 1 signal. For propene, it will display 4 signals. For CH₂ we have equivalent hydrogens. Hence, we should expect 1 signal. For CH₂ we have non-equivalent hydrogens. Therefore, we should expect 2 signals. So the big idea is this. Same connectivity is still a very useful starting rule, but in alkenes, it can fail because geometry matters. Once cis and trans relationships become different, the proton environments can become different too. In the next video, we can look at another important exception, the effect of a nearby chiral center.